Good morning, everybody. Today, I will discuss a very important term named compending. Okay. Now, in general, the compending is the summation of uh, two words, namely compression and then expansion. Okay. Now, in last class, we have discussed two important terms, that is uniform quantization and non-uniform quantization. And in case of the uniform quantization, the step size remains same throughout the input range. But in case of the non-uniform quantization, the step size varies according to the input signal value. That means uniform quantization means step size remain constant throughout the input range, but in case of the non-uniform quantization, step size varies according to the input signal value. Okay. Now, how we define the term the compending? The use of a non-uniform quantization is equivalent to passing the baseband signal through a compressor and then applying the compressed signal to a uniform quantizer. Okay, you just follow the block diagram. Just follow the block diagram. Here, it is clearly indicating that the use of non-uniform quantization is equivalent to passing the baseband signal through a compressor and then passing the compressed signal through a uniform quantizer. Okay. Now, what is actually happening? Compending is used. Why compending is used? Actually, compending is used to improve the signal to noise ratio. Compending is used to improve the signal to noise ratio, or you can say signal to quantization noise ratio, because here noise means quantization noise. Okay, signal to quantization noise ratio of weak signals. Okay, and we know that the quantization noise power can be defined as del square by 12. It is fixed. Okay, quantization noise can be defined as del square by 12. Here and suffix q means the quantization and del means step size. Okay, step size. Del means step size. We have several times go through this term, important term del, that is representing the step size. Okay, and S by N equal to signal to noise ratio. Signal to noise ratio. But here we will consider signal to quantization noise ratio, because noise means here quantization noise. That is why S by N equal to signal power by quantization noise power, or signal to quantization noise ratio. Okay. And quantization noise is defined as del square by 12. Okay. Now, we know that in uniform quantization, step size is fixed and the quantization noise power is also remain constant, because signal power by noise power. Okay, step size remain fixed. That means quantization noise power is remain constant, but the signal power is not constant, because N means noise, noise means quantization noise. Here del square by 12 is fixed, but signal power is not fixed. Okay, the signal power is not constant. It is proportional to, why not constant? We know signal power is proportional to the square of the signal amplitude. Square of the signal amplitude. That means we know P equal to V square by R. S means the signal power. P equal to V square by R. Here V means the voltage or amplitude of the signal. Okay. P equal to V square by R. V means the voltage or amplitude of the signal. Now, if the signal is varied, so what will be happen? So the signal power will be small for the weak signal. Weak signal means having low amplitude. Okay. So the signal power will be small for the weak signal, but quantization noise power is constant. This is the del square by 12. So signal to quantization noise for weak signals is very poor, and this affect the quality of the signal. Now, the compending is a term derived from the two words which we have already told, that is the compressing and expanding. Okay, this compressing technique is take place at the transmitting end, and the expanding process is take place at the receiving end. And it is very difficult to implement the non-uniform quantization because it is not known in advance for all of us that the change in the signal level, we cannot guess it in advance, the nature of the signal level. Therefore, in general, particular method is used. In general, okay, a particular method. What is that method? The weak signal are amplified and the strong signal are attenuated before applying them to a uniform quantizer. Okay, a common rule we follow, that is the weak signal are amplified but the strong signal are attenuated before applying them to a uniform quantizer. Okay, and this process is known as the compression, and this process is known as the compression, and that is take place at the transmitting end. Okay, it is very clear because we cannot say in advance the nature of the signal. It is very difficult to implement the non-uniform quantization because it is not known in advance about the change in the signal level. So we in general follow a method, that is the strong signal is attenuated but the weak signal is amplified. Okay, and this process is known as the compression, and which takes place at the transmitting end. Now, what is happening in case of the receiving end? And that is the completely opposite, which is happened in the transmitting end. At the receiving end, exactly opposite method is followed, which is called the expansion. Okay, the circuit used for providing expansion is called an expander. Okay, the circuit used for providing expansion is called an expander. The compression of the signal at the transmitter and the expansion at the receiver is combined to be called companding. That is, the companding means the summation of compressor and expander. Companding is the summation of compression and expander and expansion. Okay, and compression take place at the transmitting end and expansion take place at the receiving end. Now we will analyze this figure, linear characteristic of the PCM system. Okay, because all of these parameters are involved with the PCM application. Whatever companding, whatever uniform quantization, non-uniform quantization, everything. Okay. Now, what is actually happening? Here, the y-axis is representing the output voltage and x-axis is the input voltage. Okay. And here, the compression curve, and this one is the expansion curve. And in this case, the receiving end, the opposite function is take place is the expansion nature, and this is the compression nature. And this dotted line is indicating the linear characteristics. Okay. Now, what is happening? So how we can explain this representation? Here, figure shows the compander characteristics, which is the combination of the compression and the expansion. It is very clear from here. Okay, combination of compression and expansion. Okay, if we individually draw the compression characteristics or expansion characteristics, what will we get? In case of the compression characteristic, the nature of the curve will be like that, like this, and the expansion will be silent. And whenever we explain individually expansion characteristics, then compression will be remain silent, and what is the nature of the curve is like that. Okay, and here we are representing the combination of compression and expansion. Okay, here due to the inverse nature of the compressor and expander, the overall characteristics of compander is a straight line. There is the straight line which is representing in terms of dot lines. Okay, this indicates that all the boosted signal means boosting means external excitation, whatever that is the changing of the signal nature. Okay, this indicates that all the boosted signal are brought back to their original amplitude. That means at the receiving end, will return back to its original nature, because at the transmitting end the compression is take place, and the receiving end the expander is take place. That means the boosted signal are just returned back to its original form. Okay, and that is the all about the graphical explanation of the compending system of PCM. Okay, here it is very important. Two term actually, especially the compending means we know the compression and expansion. This one take place the transmitting end, this is the receiving end, and we know S by N means signal to noise ratio, and condensation noise is defined as del square by 12. Here the signal power is always fluctuate, and but the noise is remain constant, because signal power is fluctuate means for the weak signal amplitude is small, very small, and the strong signal amplitude is high. But we know signal power is represented P equal to V square by R. So V means the voltage or amplitude, and that is why uh, the signal level is always vary. And to get rid of this situation, we amplify the weak signal and the amplify the weak signal and attenuate the strong signal in general. Okay, and this process is known as the compression. Okay, and the receiving end, the completely opposite function is take place, which is known as expansion. Okay, and this is all about the compending curves or compending nature in a PCM system. And in the next class, I will discuss two very important law which is associated with the compending techniques, which is known as mu law and a law. Mu law and a law, and this is known as the compressor characteristics. Okay, and next class I will discuss these two important formulation, that is the regarding the mu law compending and the yellow compending, that is also important. And if there is any problem, there will be online classes will be take place, you can ask me over there. Okay, thank you all.